Dear students, now we are going to discuss a problem on double pipe heat exchanger, especially in a LMDT. So listen, here it is a double pipe heat exchanger. What is mean a double pipe heat exchanger? First, you know. So it's a double pipe means this is the first pipe. So in the pipe, the hot fluid is flowing. The first internal pipe, the hot fluid is flowing. Then outer pipe that is surrounded, that is called as the annulus pipe. This is in the then the cold fluid is flowing. So either that may be flow in same direction or in the opposite direction. So there is a first pipe, there is inner pipe, there is called as a outer annulus pipe. So we call this two pipe in one single axis we can do, that is called as a double pipe heat exchanger. Then next we discuss about the LMDT. How we choose a LMDT for this heat exchanger problems. Let me move to the problem. From that we know how we can choose the LMDT method this problem. Okay, listen. So basically, we have two methods. One is nothing but that is called as a LMDT. Then another one is called as the NTU method. Here we choose LMDT method. We can discuss that. So in that problem, first we note the conditions of the problem. Here the heat fluid, that is a hot oil with a capacity rate of 2500 watt per Kelvin. You know what is the capacity rate? I will tell you later. That flows through a double pipe heat exchanger. It enters at 360 degrees Celsius and leaves at a 300 degrees Celsius. Listen, here that is called as a hot oil. The hot oil that may be flow inside hot oil. That maybe enters at a temperature of say that is called as a 360 degrees Celsius and leaves at the temperature that is called as 300 degrees Celsius. The next, cold fluid enters at a temperature of what 30 degrees Celsius and leaves at a 300 degrees Celsius. Now the cold fluid that is the T1, then small T1 that is a cold fluid enters at a temperature of 30 degrees Celsius and leaves at a temperature of that is called as a 200 degrees Celsius. If the overall heat transfer coefficient is 800 watt per meter square Kelvin, that is represented by means of this is called U. Determine the heat exchanger area required. We need the A for parallel flow and counterflow. Here first we know what is meant by parallel flow. In a parallel flow means so the direction of hot and cold fluid, that is the direction of that is called as a cold fluid, and similar the direction of hot fluid is in the same direction. So both the fluid are in same direction. We can say that is called as the parallel flow. Okay, so the schematic diagram shown here is mainly for a parallel flow, fluid flow in a same direction. Okay, here the hot fluid temperature T1 is 360, entry temperature of hot fluid, then exit temperature of hot fluid is 300 degrees Celsius. Then we have a cold fluid, the cold fluid entry temperature is 380 degrees Celsius, it is at 200 degrees Celsius. Here for conversation we note that the T1 that is equal to that is a 30 degrees Celsius, then T2 which is equal to 200 degree Celsius. Similarly for a hot fluid we can note that the temperature T1 which is equal to 360 degrees Celsius, then leaving temperature which is equal to 300 degrees Celsius. So the hot fluid that is called as a hot oil. In the cold fluid, the fluid is that is called as a that is not given here. That is the cold fluid is here. So here we note that what is the reason for choosing LMDT. So for LMDT, out of four temperatures, that is the condition number one. Sorry, out of four temperatures, listen. So there is a 1, 2, 3, 4. Out of four, any three temperatures given, we can choose the LMDT method. Otherwise, in a problem specifically solved with the help of LMDT method, we can go definitely LMDT method. Otherwise, if a three temperatures out of four, so any three out of four temperature is given, we can choose the LMDT. Or if 2 out of 4 temperature is given, we can go to the NTU method. Here the inlet temperature of hot fluid and inlet temperature of cold fluid is given. We doesn't know the exit temperature of hot and cold fluid, we can move to the NTU method. So here in that problem, so LMDT method is called as a preferable. Okay. So first we are going to find the area for heat exchanger area for the parallel flow. So before that we move to the data book. Listen, data book for heat exchanger area calculations. Here, in the heat exchanger, there is heat exchanger Q is equal to UA delta T Lm. So for it is a single pass parallel flow, we know there is a U is the overall heat transfer coefficient, A is the surface area, delta T Lm. So delta T Lm is given for the parallel flow, same delta T Lm is given for the counterflow. We copy the things and paste it in the presentation for our convenience. So here T1 represent there is a hot fluid inlet, capital T2 represent hot fluid exit, and small t1 represent cold fluid entry, then T2 represent cold fluid exit. Okay, now this is copied and pasted in the presentation. I move to the presentation. So from the formula we can note that there is a Q is equal to there is a UA, that is a delta T Lm. Lm represent this is logarithmic mean temperature difference, so that is a delta T Lm. So for LMTD method we can use that for Lm. Okay, so U is given in the problem, then A is not given, delta T Lm. So delta T Lm that many calculated using this formula. So here, so delta T Lm that is written as, so delta T Lm which is equal to T1 minus T1 minus of, that is a T2 minus, there may be some error, T2 divided by ln of T1 minus T1 divided by T2 minus T2. We already know, so here's some error here. So here for our convenience we can take this as the, that is called as a delta T1, this is a delta T2 here also. So from that equation you may written as the delta T Lm is equal to, so delta T1 minus delta T2 divided by ln of delta T1 by delta T2. So this can be written as, that is called as a delta T1. I think there is an issue. So this can be written as, that is a delta T2. Here delta T1 and delta T2. So what is a delta T1? What is delta T2? Here note that, so the difference between these two level, that is called as the delta T1. So which is equal to T1 minus T1. So T1 is 360, then T2 is, so small t1 is 30. So the delta T1 which is equal to 330 degree Celsius. Please note that. So delta T1 is equal to T1 minus T1. So 360 minus 30 we can be written as 330 degrees Celsius. That is a delta T1. So what is delta T2? The difference between these two, that is equal to delta T2, which is equal to capital T2 minus small t2. So capital T represent hot fluid, small t represent the cold fluid. So it is equal to 300 minus 200. We can get that, that is delta T is equal to 100. So delta T1, delta T2 we can easily find. When substitute the delta T1, delta T2 in the LMTD equation. Okay. So for delta T Lm we can find, which is equal to 330 minus 200 divided by ln of 330 divided by 200. Finally we can get that there is a delta T Lm which may be, there may be around, that is equal to 190, sorry 100, there is not a 200, there is a 100. So that is equal to almost 192.64 degrees Celsius. So you already you know, then delta T Lm you know. You doesn't know, it is a Q and A. So find how we can find the Q. Listen, how we can find the Q. So in that problem, the Q can be easily find by sensible heat conditions. So here the hot fluid is flowing. So how much amount of hot fluid heat carried by the hot fluid is equal to mass of hot fluid into specific heat of hot fluid into, that is a inlet temperature minus exit temperature. Or similarly you can find the heat transfer by cold fluid, so which is equal to mass of cold fluid into specific heat of cold fluid into, that is outlet temperature of cold fluid minus inlet temperature of cold fluid. Here we know T1, T2, T1, T2, but we doesn't know the mass of the cold fluid. Here the cold fluid temperature only is given. Here the problem, the specific heat or mass, anything not given. But for a hot fluid, the temperature given, but one term is given. So what is that one term? So here that is 2500 watt per Kelvin. So that is called as a capacity rate. So capacity rate, that is called as these two terms mH and Cph, that is called as, you can written as, that is called as a CH. So CH is equal to mH into, that is Cph. So mass of hot fluid into specific heat of hot fluid, so which is equal to 2500 watt per, that is called as Kelvin. So this is called as heat capacity, otherwise that is a capacity rate. So mass of fluid, that is written as, that is a kilogram per second in mass flow rate, then in its specific it is kilojoule per, that is kilogram Kelvin. Kilogram gets cancelled, kilojoule per second, that can be written as, that is a kilowatt divided by Kelvin, but in that problem it can be written as watt per Kelvin. Now we substitute here. So this sorry, in the cold fluid that is not given. So here the parameters given. So that mH is equal to, substitute here. So QH is equal to mH into Cph into T1 minus T2. Here this is given as, that is called as a 2500 watt per Kelvin into T1 is equal to, you can substitute in the Kelvin or degree Celsius because it's a per degree or per Kelvin. So the difference is 360 minus 30. It is written as, that is a 300 Kelvin. That is a 300 degrees Celsius. So here watt per Celsius or watt per Kelvin both are same because per degree change in Kelvin is equal to per degree change in Celsius. So finally you are getting, that is a QH, that is equal to, 15,000 almost. That's right. 15,000 something kilowatt. For convenience, we can be written as, so it can be written as, there is a 150 kilowatt. So Q is also fine. What is the unknown parameter A? How we can find the A? So here A is equal to, I am right here, does note that here A is equal to, is wait, here A is equal to, from that equation you can, A is equal to Q divided by, that is U into delta T Lm. So already you find Q is equal to 150 kilowatt. You already know that is 800 watt per meter square Kelvin. Battery can be converted into kilowatt per meter square Kelvin. So that is 800 in terms of kilowatt. Now it can be written as, it is a 0.8 kilowatt per kilowatt something into, then delta TLM we can find that is equal to 192.4. So finally you can, after substituting the value, you can get the value is equal to area point 0.373 meter square. So that is the area. So area is equal to, area finally you got is equal to 0.973 meter square for a parallel flow heat exchanger. For similar condition of inlet temperature and outlet temperature, flow is a counterflow. What may be the area required? That we discuss in the next line. Here this is the counterflow heat exchanger. In the counterflow heat exchanger, hot fluid is flowing in the direction where the cold fluid that may be flowed in the, that is called as opposite direction. So that's why we call as a counterflow heat exchanger. Here also note that in the cold fluid, the temperature, that is small T1, that may be entered at a temperature of, say, that is equal to 30 degrees Celsius and leaves at a temperature of, say, 200 degrees Celsius. Here the hot fluid enters in the temperature. So here the cold fluid that may be given as, that is called as a 30 degrees Celsius, and this is flowing in this direction. So it leaves at a temperature of, say, that is a 200 degrees Celsius. Here a hot fluid that may be entered in a temperature of, say, that is a 360 degrees Celsius and leaves at a temperature of, say, that is called as the 300 degree Celsius. In the previous class I made some mistake. Oh, it's a correct. Okay, 300, not 300. Okay, correct. 300 degree Celsius. Here also you note that same counterflow we are having delta TLM. We have that is a formula, that is a Q is equal to UA into delta TLM. So, but delta TLM use a counterflow, there may be slight difference. Here also you get that is a delta T1 1 minus that is a delta T2 divided by delta T1 divided by that is a delta T2. Here delta T1 and delta T2, that is a delta TLM, so it is equal to delta T1 minus delta T2 divided by ln of delta T1 and delta T2. Here the delta T1 and delta T2 differs slightly from the parallel flow. Here also the difference that is equal to that is a delta T1. Here the difference is delta T2. But the delta T1 difference is T1 minus T2. Here the delta T which is equal to difference is T2 minus T1. So that is the difference here. Okay. Then here T1 minus T2 which is equal to T1, that entry temperature which is equal to 300 degrees Celsius, sorry 360 degrees Celsius, and leaves at a temperature of say 300 degrees Celsius. Here the temperature of T1 minus T2, so which is equal to 360 minus 200, which is equal to 160 degrees Celsius, so which is equal to delta T1. But previous case delta T1 is here delta T1 is 330, but in that case sorry, delta T1 is equal to 160. For similarly we can written as 300 minus 30, so delta T2 is equal to what, 270 degrees Celsius. So you can substitute the delta T1, delta T LMTD. So delta T1 which is equal to 160 minus what, 270 divided by ln of 160 divided by 270. So finally we are getting that is a delta T LM for the counterflow heat exchanger, that is equal to 210.22 degree Celsius. So finally we have a heat transfer equation. So Q is equal to that is a U A into delta T LM. So already you know the heat transfer coefficient, heat transfer delta T LM. Finally doesn't know the A. So A is equal to there is a Q divided by U into delta T LM. So Q already you find, because you can be find out from the Q previously, so which is equal to what, that is a Q is equal to mH into CPH into delta T. So this mH and CPH is equal to, that is called as a CH into delta T. C is heat capacity, delta T which is delta T which can be written as T1 minus T2 for a hot fluid. So after substituting the value of CH, that is equal to 2500 into the temperature difference, that may be around, that is called as a 60, you are getting Q is equal to 150 kilowatt. So substituting that is a 150 kilowatt divided by 2500 watt per Kelvin. Here delta TLM, that is equal to 210.22 degrees Celsius. Already I told, so per degree Kelvin is equal to per degree Celsius. So we can write 2500 watt per Kelvin or 2500 watt per degree Celsius. So both are per value. So after substituting the valuation, we are getting the area is equal to 0.892 meter square. So here for parallel flow, the area required is that is equal to 0.973 meter square for counterflow. The area required is 0.892, that is called meter square. So for same inlet and outlet condition, for same mass flow rate and same specific heat of fluid, so counterflow heat exchanger is preferred, because in many industrial applications counterflow heat exchanger is preferably used when compared to parallel flow heat exchangers. Okay. Thank you. If you have any queries in this topics, please give in the comment box. So in next problem, I will solve about the NTU method. This is slightly different from the LMDT method. So here the problem, in the problem you may consider some one important factor is that is called as a delta TLM. So whether it is in the parallel flow or counter flow. So for your convenience, first you draw the simple diagram and then you draw this temperature length diagram, so which is easily find the delta T1 and delta T2. So this gives you clear understanding, and this way of giving way of producing this diagram will help you to avoid any mistakes during the calculation of delta T1 and delta T2. Okay, thank you.